June 13, 1944, a coastal observation bunker near Calais, France. The night sky tears open with fire. From the concrete launch ramp carved into the French hillside, the first V-1 flying bomb ignites its pulse jet engine and screams into darkness toward England. The sound is unlike anything warfare has produced before, a mechanical stuttering roar that pulses at 46 cycles per second, a rhythm that will soon haunt London's nights like an industrial heartbeat of terror. German technicians in the bunker watch their instruments, recording trajectory data, fuel consumption rates, time to target. They have launched vengeance upon their enemy, a weapon so advanced that no defense can stop it. The Vergeltungswaffe, the retaliation weapon, carries a ton of high explosive at 400 miles per hour, guided by a simple mechanical autopilot that counts propeller rotations to determine distance traveled. When the count reaches the predetermined number, the engine cuts off, the bomb dives, and everything below ceases to exist. The officers smile. They calculate that each V-1 costs roughly 5,000 Reichsmarks to produce, about the price of a small automobile. The British will spend millions trying to stop them. Mathematics favors Germany now. Terror has become economical. But 3,000 miles across the Atlantic, in a laboratory at Johns Hopkins University Applied Physics Lab in Maryland, another group of engineers has already made the V-1 obsolete. They simply do not know it yet, and neither do the Germans. The device sits in a shell casing no larger than a standard anti-aircraft round weighing less than 4 pounds, containing vacuum tubes, capacitors, and a miniaturized radio transmitter receiver that represents the most sophisticated electronics package ever mass-produced for military use. It is called the VT fuse, officially the variable time fuse, though the engineers privately call it the proximity fuse, because that describes what it actually does. This tiny mechanism contains within its brass housing the power to end the era of the pilotless bomb, to transform anti-aircraft warfare from statistical probability into near certainty, to render worthless the hundreds of millions of Reichsmarks that Germany has invested in its vengeance weapons program. The Germans launching V-1s across the Channel in June 1944 operate under assumptions that have governed aerial warfare since its inception, that shooting down aircraft or missiles requires direct hits or extremely close proximity, that anti-aircraft fire succeeds through volume rather than precision, that defenders must fire hundreds of shells to achieve a single kill. These assumptions have held true throughout the war. British anti-aircraft batteries defending London fire conventional shells equipped with timed fuses, mechanical devices set to explode at predetermined altitudes based on calculations of target height and speed. The system requires that the shell explode within roughly 30 feet of the target to inflict damage through shrapnel dispersion. Given the speeds involved, the margin of error is impossibly small. Against the V-1, these conventional methods prove maddeningly ineffective. The flying bomb travels too fast for easy tracking, too low for optimal engagement, and its small profile presents a difficult target. British gunners fire thousands of rounds in the first weeks of the V-1 campaign, achieving kill rates below 5%. The Germans note this with satisfaction. Their calculations appear validated. The weapon is cost-effective not because it cannot be stopped, but because stopping it consumes resources vastly disproportionate to its construction cost. What German intelligence fails to detect is the revolution occurring in Allied anti-aircraft doctrine during these same weeks. In early July 1944, American-manufactured shells equipped with VT fuses begin arriving at British gun emplacements defending against the V-1 threat. The gunners receive new ammunition with minimal briefing. They are told only that these shells have special fuses that will improve effectiveness. Security surrounding the proximity fuse remains absolute. Even the gun crews do not fully understand what they are firing. The first V-1 destroyed by a VT-fused shell disintegrates in midair, on July 17, 1944, caught by a shell that exploded itself automatically when it passed within 20 feet of the target. The gunner who fired it reports a clean kill with unusual certainty. Then another, then another. Within days, the kill rate against V-1s jumps from 5% to over 60%. Within weeks, it reaches 75%. The German launch sites continue their operations, unaware that the strategic equation has inverted. They are now spending 5,000 Reichsmarks per V-1 to give British gunners target practice, with weapons the British can afford to fire in unlimited quantities. The proximity fuse represents one of the most significant technological achievements of World War II, yet it remains almost unknown even today because of the security classification that surrounded it throughout the war and for years afterward. The basic principle seems simple in retrospect. The fuse contains a miniature radio transmitter that broadcasts a signal continuously as the shell flies through the air. When the shell approaches any large metal object, an aircraft, a V-1, even the ground, the radio waves reflect back to a receiver in the fuse. As the shell gets closer, the strength of the reflected signal increases. When that signal reaches a predetermined threshold, indicating proximity to the target, the fuse triggers detonation. This principle, simple in concept, required solving dozens of engineering challenges that pushed the boundaries of 1940s electronics technology. The entire mechanism had to fit inside a standard anti-aircraft shell, had to survive the shock of being fired from a gun, accelerations exceeding 20,000 times the force of gravity, had to function reliably at altitudes up to 30,000 feet, in temperatures ranging from minus 40 degrees to plus 120 degrees Fahrenheit, and had to cost little enough to manufacture in quantities of millions. Additionally, it had to be fail-safe, incapable of premature detonation, immune to jamming or interference, and simple enough that ordinary production workers could assemble it without specialized training. The development program began in 1940 when British scientists shared with their American counterparts the problems they faced with conventional anti-aircraft fuses. Mechanical time fuses required accurate range estimation and were useless against maneuvering targets. Contact fuses required direct hits, which occurred too rarely to be militarily significant. The theoretical solution, a fuse that could sense proximity to a target and detonate automatically, had been proposed as early as the First World War, but the electronics technology needed to build such a device did not exist. By 1940, vacuum tube technology had advanced sufficiently to make the concept theoretically feasible. A team at the National Bureau of Standards, working with engineers from various universities and electronics companies, began the development program that would eventually produce the VT fuse. The challenges they faced would have seemed insurmountable to earlier generations of weapons designers. Vacuum tubes of the era were fragile glass devices designed for laboratory or radio equipment, completely unsuitable for the violent environment inside an artillery shell. The engineers had to redesign every component, creating ruggedized vacuum tubes with metal filaments that could withstand massive shock loads, designing circuits that could function with components miniaturized to a degree unprecedented in electronics engineering. The transmitter-receiver circuit operated at a frequency around 180 MHz, requiring components precise enough to maintain stable operation despite extreme physical stress and temperature variation. The power source presented another challenge. The fuse needed a battery compact enough to fit in the available space, yet powerful enough to operate the circuitry for the duration of the shell's flight, typically 30 to 60 seconds. Engineers developed specialized batteries using reserve electrolyte systems that activated upon firing, providing power only when needed. Perhaps the most elegant engineering solution involved using the setback force from firing, that brutal 20,000 G acceleration, to perform multiple functions simultaneously. The force armed the fuse by completing the firing circuit, activated the battery by rupturing membranes that allowed electrolyte to mix with active elements, and set a mechanical timer that prevented detonation for the first few seconds of flight, ensuring the shell was safely away from the gun before the proximity. Sensing became active. By 1942, the VT fuse had progressed from laboratory prototype to production model. The first manufacturing contracts went to firms including Raytheon, Sylvania, and Eastman Kodak, companies that had electronics expertise but no previous experience with ordnance. Production lines had to be established, workers trained, quality control procedures developed for a product whose failure rate had to be kept below 1%, or the entire system would be militarily useless. Eventually, over 70 different companies participated in VT fuse production, manufacturing components and assemblies that came together in final assembly plants operating around the clock. The security surrounding the fuse was unprecedented. Workers in manufacturing plants assembled components without being told what they were building. Shells equipped with VT fuses were painted with distinctive markings and subject to special handling procedures. Most critically, the fuses were initially forbidden for use over land, where duds could be recovered by enemy forces and reverse-engineered. For the first 2 years of production, VT-fused shells could be fired only over water, where any dud would sink and remain unrecoverable. This restriction meant that the proximity fuse, despite being available in quantity by early 1943, saw limited use during the first year of production. It was deployed with the U.S. Navy for anti-aircraft defense of ships, where the overwater restriction presented no problem. In that role, it proved devastatingly effective. Japanese pilots attacking American carriers in 1944 encountered anti-aircraft fire that seemed impossibly accurate, shells that exploded precisely at their altitude as if guided by sorcery. Kill rates for anti-aircraft guns equipped with VT fuses increased by factors of 3 to 5 compared to conventional ammunition. A weapons system that had previously relied on creating walls of exploding shrapnel through which aircraft might fly now could engage individual targets with reasonable probability of success. The Japanese, analyzing their mounting losses, concluded that American radar fire control had achieved unprecedented accuracy. They never suspected that the shells themselves contained guidance mechanisms. German intelligence, receiving reports from Japan about American anti-aircraft capabilities, similarly attributed the effectiveness to improved fire control systems rather than to the ammunition itself. This misunderstanding proved crucial because it meant that neither Axis power developed adequate countermeasures or adjusted their tactical doctrines to account for the new weapons. The Battle of the Bulge in December 1944 marked the first large-scale use of proximity-fused shells over land. The restriction had been lifted when Allied commanders concluded that the rapid Allied advance through France had eliminated any possibility of the Germans recovering and analyzing duds. During the German offensive, American artillery units defending against massed infantry and armor attacks discovered that VT-fused shells, which had been developed for anti-aircraft use, proved equally devastating against ground targets. When set to detonate at a predetermined height above the ground, typically 20 feet, the proximity fuse created air bursts that sprayed shrapnel downward over a wide area, far more lethal against exposed infantry than shells that detonated on impact. German troops attacking through the Ardennes forest encountered a new and terrifying phenomenon. American artillery shells exploded in the air above them with uncanny precision, raining shrapnel through the forest canopy, with an effect that foxholes and shallow entrenchments could not protect against. The psychological impact rivaled the physical casualties. Soldiers could understand and accept the risks of normal artillery fire. Shells that hit the ground and exploded could be survived through proper cover and dispersion. But shells that exploded overhead, that seemed to hunt for them in the trees, created a sense of vulnerability against which no defense existed. Brigadier General Anthony McAuliffe, commanding the 101st Airborne Division during the siege of Bastogne, later stated that proximity-fused artillery shells were the most important new development in ground warfare during the entire campaign. German after-action reports from the Ardennes offensive contain repeated references to unusually effective American artillery fire, though German intelligence never determined the cause. The reports describe American shells that exploded at treetop height with excessive effect against personnel and recommend dispersal and deep entrenchments that the tactical situation made impossible to implement. But it was against the V-1 flying bomb that the proximity fuse achieved its most strategically significant success. When the V-1 campaign began in June 1944, British defenses faced a weapon that seemed almost perfectly designed to defeat conventional anti-aircraft measures. The V-1 flew at low altitude, typically below 3,000 feet, where it was difficult to track and engage. Its speed of approximately 400 miles per hour gave defenders only seconds to calculate firing solutions. Its small size made it a difficult target for visual acquisition and tracking. Most importantly, its mechanical nature meant it could not be deceived by tactics that worked against human pilots. It simply flew its predetermined course at constant speed and altitude until it reached its target or ran out of fuel. The initial British defensive response involved fighters, anti-aircraft guns, and barrage balloons, arranged in 3 defensive zones between the French coast and London. Fighter aircraft attempted to intercept V-1s over the Channel or immediately after they crossed the coast. Those that evaded fighters encountered anti-aircraft belts positioned to create walls of exploding shells. Finally, barrage balloons tethered at altitudes the V-1s had to traverse posed a passive obstacle that could destroy missiles through collision. This layered defense achieved modest success rates, but at enormous cost in ammunition, aircraft fuel, pilot hours, and barrage balloon maintenance. The introduction of VT-fused ammunition transformed the anti-aircraft component of this defense from a probabilistic barrier into an effective killing zone. Gun crews who had previously fired hundreds of rounds per kill now achieved 1 kill per dozen rounds or less. The improvement came not just from increased hit probability, but from the psychological advantage of rapid feedback. Conventional anti-aircraft gunnery involved firing at targets and hoping that some shells exploded close enough to cause damage, with results often impossible to observe. Proximity fuses provided immediate, visible confirmation of effectiveness. V-1s exploded in spectacular fireballs when VT-fused shells detonated nearby, giving gun crews confidence that encouraged better performance and more aggressive engagement. By August 1944, the anti-aircraft belt defending London had become so effective that more than 75% of V-1s attempting to reach the city were destroyed before arrival. The Germans responded by increasing launch rates, throwing more missiles at the defensive barrier in hopes of saturating it. This response played directly into Allied advantages, forcing Germany to consume scarce resources, producing weapons that were now being destroyed reliably and efficiently. Each V-1 shot down represented not just the loss of the missile itself, but also the fuel, explosives, and labor invested in its construction, plus the aircraft or train transportation required to deliver components to launch sites. German technical intelligence attempted to analyze the dramatic improvement in British anti-aircraft effectiveness, but reached incorrect conclusions that reveal the limitations of their understanding. Intelligence reports from this period attribute the improved defense to enhanced radar systems, better gun-laying mechanisms, and concentrated defensive deployments. Some reports suggest that the British had developed new types of proximity-fused ammunition, but these reports describe imagined infrared or acoustic sensors rather than the radio frequency system actually in use. The Germans never comprehended that the Allies had mass-produced and deployed miniaturized radio transceivers in artillery shells by the millions, because such an achievement seemed beyond practical possibility given the manufacturing technology of the era. This intelligence failure had strategic consequences. Had the Germans understood the nature of the proximity fuse, they might have attempted several countermeasures. The fuse could potentially be jammed or deceived through radio frequency interference. V-1 airframes could have been modified to reduce radar cross-section or to carry simple electronics countermeasures. Launch sites could have concentrated their attacks into shorter time windows to attempt saturation of defenses. Most importantly, resources devoted to V-1 production might have been redirected to weapon systems against which the proximity fuse offered no advantage. Instead, the V-1 program continued through the fall of 1944, consuming resources while achieving diminishing returns as Allied defenses became progressively more effective. The symbolic object that embodies the proximity fuse's significance is the vacuum tube itself, that fragile glass envelope containing heated filaments and electron flows that enabled the electronics revolution. Before the war, vacuum tubes existed in radios, early computers, and laboratory equipment, but they were delicate devices unsuitable for any application involving physical stress. The transformation of the vacuum tube from a fragile laboratory component into a rugged weapon that could survive artillery firing represented a fundamental shift in the relationship between electronics and mechanical systems. German engineers examining captured American equipment throughout the war repeatedly expressed astonishment at the miniaturization and ruggedness of American electronics. German radio equipment of equivalent capability was typically larger and heavier than American equivalents, built to looser tolerances, less reliable under field conditions. This gap reflected differences in manufacturing philosophy and capability. American industry had embraced mass production techniques that emphasized interchangeable parts, statistical quality control, and simplified designs optimized for rapid manufacturing. German industry retained craft traditions that produced individually excellent products but could not match the scale and consistency of American production methods. The vacuum tube in the VT fuse represented the extreme expression of this American manufacturing philosophy. Each fuse contained 5 miniature vacuum tubes manufactured to tolerances measured in thousandths of an inch, tested to survive shock loads that would destroy any conventional tube, and produced in quantities of millions with failure rates below 1%. The tubes were designed for a service life measured in seconds rather than years. They had to function perfectly for 60 seconds of flight, nothing more. This design-for-purpose approach allowed engineers to eliminate features needed for long-term reliability and focus entirely on the extreme requirements of the firing environment. Production of proximity fuses peaked at over 1 million units per month by the end of 1944, a manufacturing achievement unprecedented in the history of electronics. This volume meant that American artillery units could fire VT-fused shells not as precious special-purpose ammunition, but as standard ordnance, available in quantities sufficient to support normal fire missions. The economic implications staggered contemporary observers. Germany had invested heavily in wonder weapons, the V-1, the V-2 rocket jet aircraft, advanced submarines, seeking technological solutions to strategic problems. America had invested in mass production of incrementally superior equipment, seeking to overwhelm through abundance rather than through individual technical superiority. The proximity fuse perfectly illustrated the American approach. It was not, strictly speaking, a revolutionary technology. The concept had been known for decades. The components, vacuum tubes, radio transmitters, batteries, all existed before the war. What was revolutionary was the integration of these components into a package that could be manufactured in millions, fired from standard guns, and used by ordinary soldiers without special training. The revolution was not in the laboratory, but in the factory. not in theoretical science, but in practical engineering and mass production. German technical intelligence reports from late 1944 reveal growing awareness that they were losing not just militarily, but technologically, not because their scientists were inferior, but because their industrial base could not match Allied production capabilities. One report, analyzing American equipment captured during the Battle of the Bulge, notes, "Enemy demonstrates consistent advantage in miniaturization and reliability of electronics equipment. This advantage appears to derive from manufacturing techniques rather than theoretical knowledge. Our industry lacks the precision tooling and quality control methods necessary to replicate enemy achievements in mass production of complex devices." This acknowledgement came too late and penetrated too slowly through a German command structure that preferred to believe in the superiority of German engineering and the eventual deployment of wonder weapons that would reverse the military situation. The V-2 rocket, exponentially more expensive and complex than the V-1, continued in production despite offering even worse cost-effectiveness against increasingly capable Allied defenses. Jet aircraft entered service in small numbers, too few to affect the air war's outcome. Advanced submarines with better underwater performance began operations just as the war ended. All of these programs represented the German approach to the technological competition, developing individually superior weapons in small quantities, rather than producing large numbers of weapons with incremental advantages. The Battle of the Bulge represented the proximity fuse's coming of age as a weapon system, but its use continued to expand through the final months of the European War. American artillery units discovered that VT-fused shells proved effective against virtually any target where airburst effects offered advantages. Against fortified positions, proximity-fused shells could be set to detonate just above bunker entrances, driving shrapnel downward into openings that direct-fire weapons could not reach. Against counterattacking armor, airbursts caught tank commanders in open turrets and disabled external equipment and optics. Against troop concentrations, the increased lethal radius of air-bursting shells multiplied the effectiveness of each round fired. The Germans adapted as best they could given their limited understanding of what they faced. Tactical doctrine emphasized deeper entrenchments, overhead cover, and dispersed formations, all sensible responses to enhanced artillery effectiveness regardless of cause. But these adaptations slowed offensive operations and increased defensive preparations, contributing to the Wehrmacht's decreasing operational mobility in the final months of the war. An army that had conquered continental Europe through rapid movement and concentration of force found itself forced into increasingly static defensive postures, partly because Allied air power controlled the skies, partly because fuel shortages immobilized mechanized units, and partly because American artillery had become too lethal to risk exposed movement or concentration. The Pacific theater saw different applications of the same technology. Against Japanese forces defending island positions, proximity-fused shells proved devastating when fired against positions on hillsides or in jungle canopy. Marines assaulting Iwo Jima and Okinawa benefited from artillery support that could suppress enemy positions in terrain where traditional artillery fire lost effectiveness. Naval gunfire support, equipped with VT fuses, could provide accurate covering fire at ranges where conventional fire control would have been guesswork. Japanese prisoners taken late in the war, when interrogated about American weapons effectiveness, mentioned artillery fire with unusual frequency. They described American shells that exploded in the air above trenches with extreme effect, and noted that traditional defensive preparations provided less protection than expected. Like their German counterparts, Japanese forces never understood the technical basis for this improved effectiveness. Intelligence reports attributed it to superior radar fire control and better quality explosives, missing entirely the revolutionary fusing system that enabled the precision they observed. The war ended before the proximity fuse's full potential could be realized in all applications its designers envisioned. Engineers had developed variants optimized for different targets and environments, low-altitude versions for use against surfaced submarines, high-altitude versions for long-range anti-aircraft fire, specialized designs for use in rockets and missiles. The fuse that had begun as a solution to the anti-aircraft problem had revealed itself as a general-purpose technology applicable to nearly any situation where precise detonation timing offered advantages. Post-war analysis confirmed what field commanders had observed. The VT fuse ranked among the most cost-effective weapons developments of the entire war. Development costs of approximately $30 million had produced a weapon system that improved effectiveness across multiple combat roles, while actually reducing ammunition consumption per target destroyed. Production costs, while higher per round than conventional fuses, were more than offset by the reduced number of rounds required to achieve results. Most importantly, the fuse had proven itself against the specific threat it was designed to counter. By late 1944, the V-1 flying bomb had ceased to be a strategic weapon because proximity-fused anti-aircraft fire destroyed the majority of missiles before they reached their targets. German technical teams investigating American equipment in the final weeks of the war discovered proximity-fused shells and attempted reverse engineering, but by then the knowledge came too late to matter. The German electronics industry lacked the manufacturing infrastructure to produce such devices in militarily significant quantities, and even if production had been possible, there were no longer adequate supplies of raw materials, skilled workers, or transportation capacity to support new weapons programs. The vacuum tubes recovered from American shells represented, to German engineers examining them, a kind of industrial magic. They were smaller than German equivalents, more ruggedized, more reliable, and produced in quantities that seemed impossible given their complexity. Each tube contained dozens of precisely manufactured components, yet they cost only a few dollars to produce. A captured American officer, interrogated about American industrial capacity, reportedly told his questioners that the United States manufactured more vacuum tubes in a month than Germany produced in a year. The Germans dismissed this as exaggeration or propaganda. It was neither. It was simply a statement of fact about the industrial disparity between the combatants. The epilogue of the proximity fuse story extends far beyond World War II into the decades of technological competition that followed. The fuse established proof of concept for miniaturized electronics in weapon systems, validating development paths that led eventually to guided missiles, smart weapons, and the entire category of precision munitions that define modern warfare. The engineers who developed the VT fuse went on to create the electronics industry of the post-war era, applying lessons learned in crash wartime development programs to civilian applications that transformed society. But the immediate lesson, the one that mattered in 1944 and 1945, was simpler and more fundamental. The proximity fuse demonstrated that democracy could innovate, could organize scientific and industrial resources, could translate theoretical concepts into mass-produced weapon systems faster and more effectively than totalitarian states that claimed efficiency as their governing principle. The fuse program involved dozens of companies, hundreds of engineers, thousands of production workers, all coordinating their efforts through voluntary cooperation rather than centralized command. The system worked because people understood what needed to be done and chose to do it, because companies competed for contracts by demonstrating capability rather than political connection, because workers took pride in producing weapons that would protect their soldiers and hasten victory. German industry, organized around cartels with guaranteed markets and political rather than competitive allocation of resources, could not match this performance. Soviet industry, even more rigidly centralized, produced vast quantities of equipment but struggled with quality control and innovation. Only American industry, messy and competitive and entrepreneurial, demonstrated the flexibility and innovative capacity to develop, produce, and field game-changing weapon systems in the timeframes that military necessity demanded. The vacuum tube sits in a display case at the Smithsonian now, removed from a proximity fuse recovered after the war, its glass envelope intact, its filaments still visible inside. The label identifies it as part of the VT fuse system, provides basic technical specifications, notes its role in defeating the V-1 threat. What the label cannot convey is the revolutionary nature of what this tiny component represented, the transformation of electronics from laboratory curiosity to practical weapon, the demonstration that sophisticated technology could be mass-produced and deployed by a democracy mobilized for total war. Children on school trips walk past this display without pausing, their attention captured by more visually impressive exhibits, fighter aircraft, tanks, bombs. The vacuum tube looks insignificant by comparison, a small glass bulb that might have come from an old radio. But that insignificance is precisely the point. This component, mass-produced by the millions, deployed in shells, fired by the millions, ended the era of the V-1 flying bomb and helped establish the material superiority that ground Axis military power into defeat. The Germans who launched V-1s in June 1944 believed they had created a weapon against which no effective defense existed. They were wrong within weeks, though they never fully understood why. The proximity fuse made their calculations obsolete overnight, transformed their weapon from terror device to target practice, rendered irrelevant the mathematics they had relied upon. They had assumed that defenders would be forced to use conventional means, timed fuses, direct hits, probability-based tactics. They had not imagined that the Americans would reinvent the artillery shell itself, would embed intelligence into ammunition, would treat electronics as a consumable commodity, to be expended in quantities that made German production seem medieval by comparison. That failure of imagination, that inability to conceive of an enemy who could afford to put miniature radio transceivers into shells fired by the tens of thousands, represented more than a technical intelligence failure. It represented a fundamental misunderstanding of what democratic industrial capitalism could achieve when fully mobilized. The Germans had built an economic system based on control, concentration, and coercion. They had convinced themselves that this system represented efficiency and would outperform the chaotic marketplace democracies they opposed. The proximity fuse, more than any single battle or campaign, proved them catastrophically wrong. In the end, the V-1 flying bomb became a symbol not of German technical prowess, but of strategic failure, a weapon that consumed resources while achieving diminishing returns, that continued in production long after it had been effectively countered, that represented the German tendency to pursue technical solutions to strategic problems created by inadequate industrial capacity. The Germans launched over 9,000 V-1s at England, expended vast resources on launch facilities and logistics, and achieved results that might have been duplicated with conventional bomber aircraft at lower cost and greater flexibility. The proximity fuse, by contrast, represented American strategic success, a weapon that multiplied effectiveness across multiple combat roles, that cost less per effect achieved than the weapons it countered, that represented the kind of incremental technical superiority that accumulated into overwhelming advantage. The fuse did not win the war by itself, but it exemplified the kind of thinking that did win: practical, innovative, focused on solving specific problems with deployable solutions rather than pursuing theoretical perfection. The vacuum tube in the museum case represents this principle crystallized in glass and metal. It is a small thing, a modest thing, a thing that seems inadequate to carry the weight of historical significance. But 5 of these tubes, properly configured, transformed anti-aircraft warfare and rendered obsolete an entire category of German weapons. Multiplied by millions and deployed by thousands of gunners who understood only that their ammunition had improved, these tiny devices helped establish the material foundation of victory. That is what the proximity fuse proved on the coasts of England in the summer of 1944, that freedom possesses its own form of technological supremacy, that democracy can organize innovation as effectively as any totalitarian state, that the voluntary cooperation of engineers, workers, and soldiers generates capabilities that coercion cannot match. The V-1 flying bombs launched from French hillsides carried terror and destruction. The proximity-fused shells that destroyed them carried proof that abundance and democracy, properly mobilized, create advantages that ideology alone cannot overcome. The Germans never knew what obsoleted their vengeance weapons overnight. They simply knew that their calculations had failed, their assumptions had proven false, and the material superiority of their enemies had grown beyond anything their economic system could challenge or their military doctrine could counter.